So chapter 7 is all about sampling distributions. Sampling distributions are when you take a sample and you get information, and then you take another sample and you get information, and then you take another sample and you get information, and you compile all that information together. So like for sample 1, let's just do proportions. Let's say I get, well, let's do means. Let's say I get a mean of, I don't know, 7 red cars in the parking lot. And then I take another sample and I get 10 red cars in the parking lot. And then I take another sample and I get 9 red cars in the parking lot. So what I have is a bunch of individual averages, and then I put all of them together and I do an average of the averages. So it's a sampling distribution. Okay, so first let's get some vocab out of the way. Population, and I refer to the population as the mothership, so this is all events. And it's a set of measurements, but it's about all events. Okay, the parameter is a measurement from the population. A parameter is a measurement from the population. So mu or sigma, they are measurements from the population, from the mothership. So it has to include everybody, not a sample. I haven't done a sample. Okay, so parameters are from the population. A sample is a subset of the population. When getting information from the population is not feasible, is too expensive, is too risky, doesn't make sense, then we do a sample. And for us, the most important samples are random samples. We want to take a good sample. Okay, now a statistic is a measurement from the sample. So statistics are measurements of the sample, and parameters are measurements of the population. For a statistic, the quantity could vary depending on which sample has been selected. I could go ask everybody in F building what your GPA is. You guys could go ask everybody in C building what their GPA is. We both took a sample. We are going to get different means. So the statistic for the sample, the average for this data could change because we're doing 2 different samples. If I'm talking a parameter, that quantity never changes because that is from the population. That's everybody. So if I went to every student at South Stokes and asked what their GPA was and found the average, and you went to every student at South Stokes High School and asked what their GPA was and found the average, we would have the same average because we both went to the population. And that would be called, that average would be a parameter. If you take a sample, it's a statistic. And that statistic could change based on whichever sample you happen to choose. All right, so we've got this vocabulary and we've got these symbols. We need to be able to throw them around and you need to be able to know what they mean. So for populations, we have mu, we have population variance, which is sigma squared. We have the standard deviation, which is sigma. And we have proportions, the proportion of free throws that I'm going to make. That's P. Now, we have a lot of P's in stats. Capital P is the probability of something happening. Lowercase p is the proportion of something that has happened. So I'm going to make 3 out of my 5 free throws. So I could find the probability that x equals 3/5 or p equals 3/5. Capital P for probability, lowercase p for proportion. Now sample statistics. Okay, so sample. So I'm taking a sample from the population, so I don't have parameters anymore, I have statistics. So your sample mean is good old X bar. Your sample variance is S squared instead of sigma squared. Your standard deviation is S, sometimes S sub X, and not sigma or sigma sub X. All right, now here's a proportion from a sample is P hat. Okay, so again we have another P. So I have a capital P, I have a lowercase p, and I have a P hat. Later we'll have a P bar. Okay, so when I say X bar, I need you to know that that came from a sample. If I say sigma squared, I need you to know that that's variance from the population. If I give you sigma, I need you to know that that's the standard deviation from the population. If I give you P hat, I need you to know that that's a proportion from a sample. If I give you a lowercase p, I need you to know that's a proportion from the population. And if I give you mu, you need to know that that's an average from the population. Okay, so population, mu, sigma squared, sigma, and p. Samples, X bar, S squared, S, and P hat. Okay, so all we're going to talk about today are sample proportions. Next class, we're going to do sample means. And everything from here out in statistics is really divided into two parts. You're going to do what we do with proportions, and then we're going to do the same thing with means. And you'll see how they're different. Okay, so we are just talking about proportions. So 3 out of 5 free throws, not average SAT score or average GPA. Those are means. We're talking about proportions. Successes over trials. What proportion of U.S. teens need to know that 1492, or not need to know, but know that 1492 was the year in which Columbus discovered America? A poll found that 210 out of a random sample of 501 American teens aged 13 to 17 knew this historical important date. So I have P hat. Now think about why it has a hat on it, because this is a sample of 501 American teens. And that's the number of successes out of the number of trials. So 210 out of 501. So P hat is 42%. P hat is the statistic that we use to gain information about the unknown population proportion P. I don't know the population proportion P. This is a parameter. This is a statistic. I don't know about the population proportion P because I can't go ask every single American teen if they know this fact. However, because another random sample of 501 teens would likely result in a different estimate. So if I went out and got 501 other American teenagers, I would not have 210 probably exactly who said that they knew that Columbus discovered America in 1492. But it would probably be close. So when I use statistics, not parameters, but statistics, I'm going to say about 42% of U.S. teens know that Columbus discovered America in 1492. If this was a P, then that would be from the population, and I could say exactly 42% of all American teens know that Columbus discovered America in 1492. Because without the hat on it, P is a parameter, and that goes to the whole population. But when it's a P hat, it's a statistic which comes from a sample. and another random sample of 500 teens would likely result in a slightly different estimate. So we're going to use the word about or roughly. We need to find out what would happen if we took many samples. This would produce a sampling distribution of p hat. So what I'm going to do is I'm going to ask every single one of you to go out and ask 501 different American teenagers this question about Columbus and record your data. So everybody's going to come back with a p hat, with their own p hat. And they're all going to be different, but they should all be in the same ballpark. So then what I'm going to do is I'm going to take all of your proportions and I'm going to find the proportion of the proportions. I'm going to add up all the kids who said that they knew this date was important out of all the kids that everybody asked and get a sampling distribution of p hat. Okay. So this example is about a candy machine, and the link here, feel free to click on it. It's really cool. It takes you to a candy machine where you can select different parameters, and it will spit out candies, and you're trying to find the proportion. I think that it's orange, that an orange candy comes out. So imagine a very large candy machine filled with orange, brown, and yellow candies. The candy company says that their orange candies, hold on, their orange candies make up 45% of the candy machine. So orange, 45%. That's what they're claiming. Suppose you draw a sample of 25 candies at one time. And so on this little link, you can go there and you can select that you're gonna I want 25 candies, and it'll tell you the proportion of them that were orange. Okay, then clear that out and do it again. Then there's also a place on there where you can tell it how many times you want it to do it. So suppose you draw a sample of 25 candies a total of 10 times. And it'll show you all the results for all 10 of them. Then you can do it 400 times. Okay, it says describe the shape, center, and spread of the sampling distribution of p hat in the dot plot. Well, if we look at this, this is, let's see, N 45, sample size 25, number of samples 400. Okay, so these dots, each dot represents pulling the lever and getting orange candies one time. Okay, so one time, and it's hard to read this, looks like there are 2 dots down here. So there were 2 samples that had very few, looks like about 15% orange candies. Well, that's very much against what the company claims. The company claims that they have 45%. Then it looks like I've got 2 up here where when I pulled the lever, I got a sample of candies that had, looks like 71, 72% were orange. Have you ever opened a bag of M&Ms? And like, let's say your favorite color is green and there's no green in there and you're so disappointed. Or brown is your least favorite because you love the colors that make you happy, and over half the bag is brown. So this company is claiming that if you pull the lever, you should get 45% orange. So what's happened is, can you see that most of the samples have an average somewhere in here? So anywhere from a 0.35 to a 0.5 or maybe a 0.55. Now if you'll notice, this sort of, kind of, maybe looks like a normal distribution. Now it's not a normal distribution because normal distribution it's fluid. It has information in between every nook and cranny. This does not. I have a very specific number of orange candies. There's no in between. Okay, now let's look at this one over here. What's changed is I've upped my sample size to 50. So I'm getting 50 pieces of candy out. I'm still wanting, the goal is to get 45% of them to be orange. But I'm doing this 400 times. Now compare. Which graph looks more normal? And it's the graph on the right. So the more samples you do, the more samples you perform, your sampling distribution, which is what these are, looks more normal. Also, if the proportion you're shooting for, like this one was 45%, the closer that is for proportion, the closer that is to 50%, the more normal your graph will look. Like if they said, hey, we've only got about 10% orange candies every time you pull that lever, then that would have a harder time looking normal. But they're saying 45%. So the closer that p-value is to 50%, the quicker this thing will look normal. Okay, so what have we learned so far about the sampling distribution of p-hat? Let's talk about the shape, the center, and the spread. The shape of a sampling distribution can be approximated by a normal curve. It's not normal. It's not. It's not fluid. But we can use a normal curve to approximate it. And the bigger the sample size, the better the approximation. If I go out and ask 20 students something versus I go out and ask 200 students something, the sample that has 200 students is more likely to be a better representation of the population of the mothership than me just going out and asking 20 people. Remember, repetition is one of our designs to a good study. So the bigger the sample size, the better the approximation. Okay, center. This is really important. The mean of the sampling distribution. Again, guys, sampling distribution, make sure you know what that is. The sampling distribution are all the information that you got from a whole bunch of samples. So you took a whole bunch of samples. You got a handful of candy a bunch of times. And each handful, you found the percent that was orange. Then you took all those proportions, all those percents that were orange, and you found the average or the p hat for all of your p hats together. So mu sub p hat, the average of all your p hats is p. Okay, now who is p? P is a parameter. He is the proportion of the population. P hat is the sample proportion. So when I find the average of all my p hats, that equals p. This makes sense because the sample proportion p hat is an unbiased estimator of p. Spread. This is really important. As n, guys, n is your sample size. Little n. Remember little n? Little n is your sample size. As n gets larger, remember asking 20 students versus asking 200 students? The standard deviation of your sampling distribution gets smaller. The more people you ask, the tighter your data gets. The less loosey-goosey your data is. As n gets larger, the standard deviation, sigma sub p hat, so the standard deviation of your sampling distribution gets smaller. The standard deviation, the wiggle room. Okay, so here's what we're going to have to do with this information. The sampling distribution of a sample proportion. Please stop and make sure that you understand the difference between those words. A sampling distribution is a distribution of a whole bunch of different samples. Of a sample proportion, one sample, singular. Choose a simple random sample of size n from a population of size n with a proportion p of success. Now, who is this? That is a parameter. He is the population proportion. Population, mothership. Let p hat, now he is a statistic, he is the sample proportion. Let p hat be the sample proportion of successes. Okay? So the average of all your p hats, because this is a sampling distribution, you're going to take a bunch of samples, and then you get all those proportions. The average of all those proportions. So the average of all of your sample proportions is the mothership proportion. It is the proportion of the population. The standard deviation of p hat, so sigma sub p hat equals the square root of pq over n. P is a probability of success, Q is probability of failure, little n is your sample size. That's on your formula sheet. But here's the kicker. You can only use this formula if this. 10% condition, which we have talked about, that's him. 10% condition means that my population is so big and my sample is so small that when I take a sample out, it doesn't necessarily drastically affect the probability of something later happening. As n increases, the sampling distribution of p hat becomes approximately normal. Stop right there. That's a very powerful sentence. Let's make sure we have that. As n increases, the sampling distribution of p hat becomes approximately normal. It's not normal, but we're going to use a normal distribution to approximate what it's going to be. But before you get the green light to do that, you have to check the LCC, the large counts condition. And the large counts condition is NP has to be greater than or equal to 10 and NQ has to be greater than or equal to 10. Now what you guys have to really make sure that you know, because they will kill you with points on this. If you're using a P that's from the population, then it's a P. But if you're using a P that's from the sample, it has to have a hat on it. Because if it's from the sample, it's p hat. If it's from the population, it's p. And the same thing with q. So you have got to be able to make sure that you are distinguishing between the two. And they will be checking that really carefully. Okay, about 75% of young adult internet users age 18 to 29 watch online videos. Suppose that a sample survey contacts a simple random sample of 1,000 young adult internet users and calculates the proportion in this sample who watch online videos. Okay, first of all, does everybody understand that we're doing a proportion and not an average, not a mean? This is, do you watch a video, online videos, or do you not, out of 1,000 people? What is the mean of the sampling distribution of p hat? So we're going to do this a bunch. We're going to take a bunch of samples. We're going to get a bunch of p hats. So I want the average of the sampling distribution of p hat. So translate that. I want the average of the sampling distribution of p hat. Well, we know from before that equals P. Mothership, P. Population, parameter, P. Now, it says in the very first sentence, 75% of young adult internet users watch online videos. It doesn't say of this sample I just took. It says 75% of young adult internet users. Okay, the explanation, the mean of the sampling distribution of p hat is equal to the population proportion. So what you're doing is you're stating in words what they've stated in statistic symbols. The mean of the sampling distribution of p hat is equal to the population proportion. Okay, then it says find the standard deviation of the sampling distribution of p hat. It's really easy to go straight to your formula, but I cannot use this formula until I know this is true. This is the gatekeeper for him. So when you come back here and it says find the standard deviation, you've got that gatekeeper going, not yet. First, you have to check your 10% condition, and you need to write and label that that's what you're doing. The 10% condition, you need to state what that is, and then you need to plug your numbers in. Well, how many's in my sample? 1,000. What's my population? It doesn't say. It doesn't say how many young adult internet users there are. So I write all, and the word all is very important because that's what shows that it's the population. All young adult internet users. Now, if 1,000 is less than 1/10 of all young adult internet users, that means there needs to be 10,000 young adult internet users. And absolutely, there are at least 10,000 of them. So I put a big old check mark right there. That will always be true. You can assume that it's always true, but you have to show it. But then you put a check mark saying, okay, I'm good. The gatekeeper has given me permission to carry on. So now, make sure you use the correct stat symbols. The standard deviation of the sampling distribution of p hat, PQ over N. Okay, so here's a question. This P and this Q that I'm getting ready to use, are they parameters or are they samples? It says about 75% of young adult users watch online videos. That's not from a sample. That's from the population. So these do not get hats on them. It is just P and Q, not P hat and Q hat, because this information did not come from a sample. So 0.75, which means my Q is 0.25. And my population is my sample size is 1,000. All right, then I want you to pause this and type that in and make sure you can type it in and get it right. And we're going 3 decimal places. And I went 4 because it starts with a 0. Okay, now it says, is the sampling distribution of p hat approximately normal? Well, right now this is not a normal distribution. These are proportions. So it's not a normal distribution, but I'm trying to see if I can use a normal distribution to approximate the sampling distribution. To see if that's true, I have to check my large counts condition. So that's NP greater than or equal to 10 and NQ greater than or equal to 10. And again, I have to do a P and Q check to see if they need hats or not. This P and Q does not need hats because the 75% is from the mothership. It's from the population. So my sample size was 1,000. The population proportion was 75%. And then I just type these in or multiply in your head. And these both pass. So yes, the sampling distribution of p hat is approximately normal. Please make sure when you write the word normal it's capitalized because it is the name of a distribution. Okay, number 4. If the sample size were 1,000 rather than, no, it were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? This is a question, I think it's on your homework, I also think it's on your test review, and I think it's on your test. If the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? It doesn't do anything with my mu, because sample size doesn't come into play there at all. But what measurement does sample size do come into play? And that's your standard deviation of the sampling. Nope. Okay, so I don't care what the top number is, but let's have 1,000 on the bottom, and then let's have 9,000 on the bottom, and let's talk about the difference. Well, if I'm going to square root it, again, I don't care what the top is. If I square root the bottom, let's see, what's a better way to do this? Think about this, okay? Isn't this that? Okay, then aren't these the same? Okay, so leave them alone. The difference is he is being multiplied by a 9 on the bottom, but that 9 is under the square root. So if I were to square root it, I get a 3 on the bottom. So I now know, not squared, that this standard deviation and this standard deviation are related somehow with this 1/3. Well, this standard deviation, when I had 1,000, equals 1/3 times that standard deviation when n was 9,000. So if the sample size were to go to 9,000 rather than 1,000, how would it change the sampling distribution? Well, guys, if it's going to take your standard deviation and multiply it by 1/3, then isn't the standard deviation of your sampling distribution getting smaller? If you're multiplying it by 1/3, by a factor of 1/3. So I looked at the 1,000 and I looked at the 9,000, and I can see that that's 9 times this one. Again, that 9's on the bottom and it's under the square root. So when I leave it on the bottom and I take it out of the square root, I don't care what all this mess gives me. It's just the fact that he has an extra 9 and he doesn't. So when I square root that extra part out, I can see that this standard deviation is 1/3 of this one. So when my n increases, my standard deviation gets smaller. Didn't we say that? That if your n increases, the wiggle room, the variability of your data gets smaller. And in this case, it gets smaller by a factor of 1/3. Okay, going to college. A polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Find the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value. First of all, state what you know. I know that P is 35% or 0.35. P with no hat, because that 35% was the population. I know that my sample size is 1,500. Okay, now let's translate the question. The question says, find the probability. Okay, now hold on a second. So I want the probability, capital P, the probability that a random sample of 1,500 students will give a result within 2 percentage points of this. So that means that's where I want to be for my sample, and that's why that P has a hat on it. Find the probability that the random sample, so I'm P hat, will give a result within 2 percentage points. So guys, you should already be picturing a curve. You should see the average of 0.35 in the middle, and I want from 0.33 to 0.37. But to do that, I need a mean and a standard deviation. The mean of P hat is P, which is 0.35. Get all your symbols, all your hats, all your decimals, all your non-hats. Get all that stuff figured out. Okay, so that's awesome. I need that. But I also need a standard deviation. What's the gatekeeper for standard deviation? It's the 10% condition. So I have to, all right, now my sample size was 1,500. What's my population? All first year college students. And that would make me have to have 15,000 first year college students? Absolutely got it. Not a problem. So now that's the gatekeeper. So now I can find him. All right, think about what his formula is. And again, that's on your formula sheet. Okay, P, not P hat. I don't know P hat, but I do know P. P is 0.35, which makes Q 0.65. And my sample size was 1,500. So there's my standard deviation. Okay, so I'm almost ready to go normal distribution on this sucker, but I need to know, can I use a normal distribution to approximate? To do that, the gatekeeper is the large counts condition. So I have to do NP and NQ with no hats, because I don't have sample information. I have mothership information. So then I go 1,500, and he has to be bigger than 10. And he has to be bigger than 10. So now I'm good. I'm a green light. So now I draw. He's 0.35. I want to go from a 0.33 to a 0.37. Shade. And then I go normal CDF from here to here with a mean of 0.35 and a standard deviation of 0.0123. So you go normal CDF that sucker, and you get that. So then you put a nice little sentence that puts your bow on top. So you say 89.61% of all simple random samples of the same size 1,500, will give a result within 2 percentage points of the true value of 35% of the population. Okay, I know that was fast and I know that was a lot, but the nice thing is you have this on video. So once you have it all written down, just stop, rewind the video, and just watch it one more time. And then dive into that homework and just know that the homework has got the little kinks that you need to work out. You need to really, really, really check your homework answers and come see me if you have any questions.